Okay, so last time we started Chinese remaindering. The theorem said that if you take two integers that are co-prime, then arithmetic modulo A and modulo B is the same as arithmetic modulo AB. And in terms of rings, it meant that the factor ring Z mod A cross the factor ring Z mod B. This as a ring is isomorphic to the factor ring mod AB. And the co-primality we saw was necessary condition. So that was the mathematical part. There is actually an algorithm also which can achieve this. So this isomorphism map is very efficient. It can be computed in log of the bit size of A times the bit size of B. Right. So in the terms of input size, bit size, it is quadratic. Any questions? So it was efficient because we actually gave a very explicit map. This map phi was, it just required computation of B inverse mod A and A inverse mod B. So in the same spirit, you can show Chinese remaindering theorem for polynomials. So if fg over a field f in one variable x are, so these are univariate polynomials and they are co-prime. Then like before, you have to look at the factor ring, right, which will be the polynomial ring modulo f, the ideal. So this is the first factor ring. The second factor ring is fx mod g. So mod f arithmetic and mod g arithmetic, this product is isomorphic to mod fg. Is that clear? So like numbers, polynomials have the similar Chinese remaindering theorem, which is that as long as they are co-prime, mod fg arithmetic can be broken into simpler arithmetic, mod f and mod g. The proof will be identical. You use the same map with f inverse mod g and g inverse mod f, and the time complexity will be to compute that the isomorphism is computable in how many f operations? Right. So you have to recall how much time f inverse mod g computation requires. So you will get this in terms of degrees. So these many f operations, which we are not going inside. So the ring operations in f, the field operations f, we are counting as unit time. On top of that, it is degree f times degree g many such operations. And here also the co-primality is important. Okay, if they are not co-prime, then again this statement is, this isomorphism equation, this will be false. That you can easily see. So if you take, for example, f to be x and g to be x, then mod x arithmetic versus mod x square arithmetic. Right, those things are very different and unrelated. Any questions? Right, so now whenever we invoke Chinese remaindering theorem, we'll just invoke one of these two, and the time complexity etc. will be implicit. Okay, we have shown that these things are efficient. So the first major algorithm that we will see in this course is how to multiply polynomials. So fast polynomial multiplication. Oh, I wanted to make another remark before. Why is Chinese remaindering theorem important in our study? So one thing is that always the motivating case will be when you take f and g to be irreducible. Okay, so you want to do arithmetic modulo f times g, which is clearly a reducible modulus, and you may not be able to study much mod fg. But when you go mod f, then since f is irreducible, this factoring is a field. Okay, so you reduce the question of rings to two fields. So the understanding over fields or in fields is far more than the understanding in rings. So this is why, in fact, that's the very reason CRT exists. That it gives you, it reduces rings to fields. So this it does both in proofs and also in algorithm. So ideally you want to work over fields, because there are more theorems over fields than over rings. More things are true over fields. Rings are harder to study. So this is one way to do that transfer. Okay, so back to this. Right, so the problem here is clear. You are given two polynomials, f and g. In some polynomial ring. So they are polynomials in one variable x. R is some base ring, and their degrees are, let's say, less than equal to L. So we are given f and g in the input, and we want to compute f times g as fast as possible. Already you know how to compute in L square operations, but now you want to do as something closer to L. Before solving this problem, we should have studied actually how to multiply integers fast. Right, that's a more basic question than multiplying polynomials. But the only reason why we are not doing that is because integer multiplication algorithms use polynomial multiplication. So somehow the machinery is better for polynomial multiplication. So we'll first do this, then we will do the more basic thing, which is integer multiplication. So actually integers are first written as polynomials, and then they are multiplied in the fast algorithms. So for that strange reason, we start with polynomial multiplication first. So we want to beat the naive L square time algorithm. So we want to beat this algorithm, order L square algorithm. So ideally you want to make it order L. Right, that may be impossible, but at this point we don't know whether it's impossible or possible, because the input size is order L, 2L. So all we know is that we will need time at least L, but we don't know how much more. So the correct complexity is between order N and order L square. So this fast algorithm will achieve something between and much closer to L than L square. So I think some of you already know the idea how this is done. So how do you do this? FFT. Yeah, but why do you go to FFT? Yes, so we change the representation of the polynomial and hence the algorithm also. So this basic algorithm is looking at the polynomials as sum of monomials, and then it is multiplying one monomial with one more monomial, one from F, one from G. So that gives you L square. Instead, you can look at a different representation, which is in terms of the values of F. So you compute F at some points, so you get some evaluations, and same with G. And then you multiply these evaluations. So you use the property that evaluation is a homomorphism. So when you multiply F alpha with G alpha, that is also the value of Fg at alpha. Right? So you use that property. That evaluation is a homomorphism, so you can actually as well work with evaluations as far as multiplication is concerned. So that's the trick. That use evaluations. And the thing with evaluation is that, yeah, so now you can recall interpolation. So interpolation tells you that for a degree L polynomial, how many evaluations do you need to uniquely specify F? Sorry, L plus 1. And if you assume F to be monic, then only L. Right? So polynomial is uniquely specified either by L coefficients or by L evaluations. Okay, so this is the second representation. We use L evaluations. Then you can multiply them, the corresponding evaluations of F and G. And but remember that in the output you have to output polynomial in the monomial representation. Right? So you have to then do interpolation again. You have to basically reverse the interpolation to get the monomial representation. So that is the sequence of steps. Change the representation, multiply, and then again change the representation back. So in the middle of this, Gauss's trick is used. Which will give the efficiency. So we'll see these things. Yeah, so what do these keywords mean? Let us now describe in more detail. So since somebody mentioned FFT, so this means that you will not take any arbitrary evaluation but some special evaluation. So what are the points at which you evaluate? Sorry? Yeah, so you will use complex roots of unity. Yes. So let us move to that. So first we make a major assumption that the base ring has those, that the base ring R already has complex roots of unity. So suppose R has a primitive Lth root of unity omega. Okay, so this may not be true because, for example, if ring was a ring of integers, then it will have the second root of unity, which is -1, but it doesn't have the third root of unity. So symbolically you are looking at this 1 raised to 1 over L, or Lth root of unity. So in general these are available in complex field, but may not be available anywhere below complex field. So we are assuming that R has whatever we need. Okay, so that's a major assumption. Usually this assumption is not worked out in other courses, but true to the name algebra, in this course we will work it out. So what do you do when R doesn't have Lth root of unity, which is actually all the time. In all practical applications, Lth root of unity will not be there in R, right? So there is a major construction that you have to do to get rid of this assumption. But let us first see the basic idea assuming this. So the idea is, after this assumption, so evaluate f and g at these points. So points being omega to the 0, which is 1, omega, omega square, and it goes up to L minus 1, right? So these are the L points. So you get 2L values in R. Then you multiply them. So omega I with omega I, f and g respectively. This multiplication will happen in the ring R. This is happening for all i's. So these are L multiplications you will do. These are L R operations. So we don't have to specify how this is done because this is in the base ring. So that we don't specify. And then you have to do interpolation. To get the product H right. So those are the 3 steps. So what is the complexity of this? If you just implement this, what is the complexity?
L square already to evaluate if we do it now.
Already in step 1, right? Because so it seems that we have not made any progress. We have just added a lot of keywords, but no progress whatsoever, because just to evaluate f at omega to the I in step 1, it takes L steps because there are L monomials to be computed and then added. So L many R operations, and then you have to do this 2L many times, because f at L points, g at L points, so this is L square, right? So there is no progress, it seems, because the coefficients of f are arbitrary. So those arbitrary multiplications you have to do.
So for interpolating h, wouldn't we need 2L coefficients? Or
That is true, yeah. Yeah, those things are there, but say you assume that L is big enough. So we started with the assumption that f and g have degree at most L. So in practice you use L by 2. So f and g are degree L by 2 each. So each is of degree L, and then we keep working with the same omega. That's just a readjustment. So the bigger problem is that this is not improving on L square, right? So so this is why just changing the representation is not enough. You have to use something called the trick of Gauss. which is a clever halving step in a recursion. Okay, so we'll actually do a recursion. So it should be compared with the merge sort. So merge sort sorting algorithm requires for L elements L square. I mean, without clever recursion it is L square, but with merge sort you halve it and then you get a recurrence formula which gives you L log L. So same thing we'll do here, same effect, but the reason will be different. So yeah, let's basically we want to do step 1 and step 3 in a faster way, in a recursive way. So those are the problems. 2 is trivial, 2 isn't the problem is 1 and 3. How to improve over L square. So say the polynomial is, I said degree L, but say this is L minus 1. So there are L coefficients, A0 to A L minus 1. The AIs are in the ring R. So let's take this as the definition of AIs. So this evaluation step, in the literature it is called discrete Fourier transform. Okay, so the discrete Fourier transform is just a longer name for evaluation at roots of unity. So we'll call it DFT omega. So DFT omega is an operator which has already taken an argument omega, and then it will take these coefficients as an argument, A0 to AL minus 1, and output the values of f at omega to the I. So A0 dot dot EL minus 1, it will map it to f omega 0, f omega L minus 1. Okay, so it takes this L coordinates and defines the polynomial f based on this, and then f it evaluates at powers of omega, which is also a parameter to the operator. So this operator is classically called discrete Fourier transform. This is what we wanted to do in step 1. Once for f, once for g. Now we want to compute this in a very fast way, not in the trivial way, but faster way. So for that we need some assumptions. So we'll assume that L is a power of 2. Why can't we do that? Why can we assume L to be a power of 2? Yes, so whatever is the degree upper bound for f and g, how far do you think is a power of 2 from that degree bound? Sorry?
Between that degree and twice.
Twice, yeah. So you just have to, maximum you have to double that upper bound. So you double it and you use that power of 2 as the new upper bound. So it is trivial. You can assume that L is a power of 2, 2 raised to n. Okay, and then for this we will give a fast method to compute the operator. So well, I think first I prove a nice property of the operator before moving to the algorithm. So let us first observe a relationship between, so DFT omega is the operator you want to study. Actually, in the algorithm idea already, you would be interested in also finding the inverse of this operator, right? Because in step 2 you multiply the values, and then from the values you want to go back to the polynomial h. So that is nothing but inverse of DFT omega. So what is the inverse of DFT omega? DFT? Yeah, nearly DFT omega inverse. So that is what we will show in this lemma, that if you compose this with DFT omega inverse, so you apply the first operator DFT omega on a vector, and then you apply DFT omega inverse. Omega inverse is simply 1 over omega, it's just this next primitive Lth root of unity. Then the composition is actually just a scaling operator. So it is L times identity. Okay, so this is just the identity transformation, linear transformation. So remember that DFT is a linear transformation. It's acting on a vector space. Is that clear from this? It should be clear from the definition in blue that this map that we have defined, this is a linear operator. So if you take this vector a bar, another vector a bar prime, right? How is the action on a bar plus a bar prime? So a bar defines a polynomial f, a bar prime defines a polynomial f prime. When you take the sum, you actually get f plus f prime, right? So the image also can be decomposed as sum. So this is a linear operator. With respect to what field, so that will depend on whether R is a field or not. So, but if R is a field, then this is a linear operator over R. Okay. Yeah, so identity is simply it sends a bar to a bar, and L times identity is that it is scaling a bar to L times a bar. Okay, that's the formula we want to show. This is an extremely fortunate formula because it tells you that inverse of DFT is again DFT. So it also has a simple similar form. So if you show that step 1 is fast, then step 3 is also fast.
What if L is not invertible? You need L, to find the inverse, you need L invertible.
Yeah, that's a good point. Why would L not be invertible? L is 2 raised to n. So what is the reason?
Like 0 divided
The characteristic of R is 2. So just rule that out. Say that the characteristic of R is either 0 or odd. And what to do with characteristic 2, that will be a simple exercise. We'll use a slightly different, we'll use just a simple trick to handle characteristic 2. Yeah, but then we are digressing, so those things are not important. Let's first prove this and go to the efficiency point. So DFT I write as a matrix product. So DFT's matrix action is you have first row is all 1, then you have 1 omega to the L minus 1 and so on. Times A0 to AL minus 1. Okay, so once written this way, it's easy to see. F1 is just sum of the AIs, and F omega is basically A0 to AL minus 1 are the coefficients defining F, right? So when you look at the left hand side, you are actually evaluating F at 1 omega dot omega L minus 1. So that is the matrix action. So what is the matrix action now of DFT omega inverse on this? So you will multiply on the left hand side, you will multiply by the matrix where you replace omega by omega inverse. So this is the following product. So this is now omega inverse. So this matrix times the above matrix. Right, and now you will with some practice, you will be able to see that the first row, all one row, when you multiply it by the first column of the second matrix, right, that will give you clearly L, but the inner product of the first row with the second column is the sum of 1 omega square omega to the L minus 1. And what is that? Why is that 0?
When we do it in complexity, we assume it is e power 2 pi I, then we prove it. How can we prove that?
Yeah, good. So then we have to prove it. So let's prove that first. So x to the L minus 1, this polynomial has factors or roots. Right, this is the factorization over complex of x to the L minus 1. What is the coefficient of x to the L minus 1? In the above. So in the left hand side it is 0, and in the RHS it is just with sign 1 plus omega dot dot. Okay. So this means that the sum of omega to the I vanishes. That's the first thing. But in the matrix product, you are also getting, when you multiply first row with the third column, take the inner product, then you will be looking at sum of 1 omega square omega 4 dot dot omega to the 2L minus 1. So what is that? So let's shorten this. So what is this equal to? Omega to the 2i. What is omega square? Is it a root of unity? But it is then L by 2th, right? So you can replace it by omega prime, or maybe we can use, we can parameterize this. So, so this was omega L. This is now, this can be written as L by 2. Okay, this is the L by 2th, because L is 2 raised to n, so this is 2 raised to n minus 1. Omega square is 2 raised to n minus 1th primitive root of unity in complex. So when you look at this sum, this will give you all these L by 2th roots of unity, possibly with, I mean, with repetition. You get 2 basically, each of these are doubled. So just like you did argument before, you can do now, you can look at x to the L by 2 minus 1, and this also will be 0. Okay. Then next will be 3i. So what is that? What is omega L cube? What is the order of this? Yes, omega L cube is just like omega L. So omega L powers will give you all the Lth roots of unity, and omega L cube also has the same property. So just the first equation can be used. So you can think of it as it's omega L some other omega L prime, some other Lth root of unity, and then you are raising it to I, which by the above argument, top argument is 0. So it's just this argument appropriately changed for the power. Okay, so for odd, the argument is the top argument. For even, like for 2, it was you bring it down to L by 2. For 4, it will be bring it down to L by 4, and so on. Okay, so this you can complete. Okay, so once you complete that, at least the first row has been handled, right? So first row you saw is L followed by zeros. What about the second row? So second row is 1 omega inverse L minus 1. Sum it up. So that sum will be, I mean, minus 1 you can think of it as L minus 1, right? Because it is on top of omega. Omega is order L. So minus 1 and L minus 1 are the same. So, and L minus 1 is odd. So by the green calculation, this will still be 0. So this will be 0. In fact, with all the columns you will get 0 except the second column. Second column will cancel minus 1 with 1. So there you will get L. And this pattern then continues and gives you the identity matrix. Is that clear? So DFT omega inverse, when you compose them, then you get scaling effect. Scaling is exactly by L. Okay. So one note is assume L to be not a zero divisor of R. That is, characteristic of R is not 2. Okay, so 2 raised to n will be a zero divisor if and only if it is actually 0. In all other cases, 2 raised to n will be invertible. So for now, you can assume characteristic of R to be not 2. When it is 2, we will see a different argument. It's a simple correction. So the reason why you need L to be invertible, so characteristic of R not equal to 2 implies that L inverse exists. So you want L inverse to exist so that this formula, lemma 1, you can say that DFT omega inverse divided by L is the inverse. You wanted that to make sense.
So the characteristic of Z6 is 6, but not 2 still.
So we want to look at L inverse times DFT omega inverse. Yes, what was the question?
So characteristic of Z6, for example, is 6, but 2 is still a zero divisor there. So
Oh,
It should not
it
even.
will not be even.
Not be even.
I guess what I mean here is that it's a field. Yeah, but there are now too many implicit assumptions. Okay, let me change this. So 2 raised to n is not a zero divisor if and only if the characteristic is odd. And when the characteristic is odd, then L inverse will exist. Let us live with this.
Characteristic can also be 0.
Yes, 2 does not divide or characteristic is 0. Right, so now we can see the Gauss's trick. How do you compute DFT faster than L square? But Gauss had a better idea. So that idea is by, as I said, recursion, but how do you recurse? Surely you have seen it, but generally you don't understand it. Do you remember it?
Even comes in the odd. Even parts not also.
So this fx monomials you divide into kind of even monomials, odd monomials, better than faster than L square. Okay, so you will be able to reduce actually both the roots of unity and the degree of the polynomial. So that is how that is what is meant by recursion. And the algorithm you have seen. So what you get after that is this statement that DFT omega can be computed in order L times log L R operations. Okay, so instead of L square, you will get L log L. So let us just implement what we discussed now. So you will write fx as even monomials. So 1 x square, x4, x6 monomials, that part and the remaining part, that's the odd part. So so even part is a function of x square and odd part is a function of, yeah, if you remove x, then it is also a function of x square. So it is this. So uniquely fx will give you f0 and f1. And then you use the divide and conquer trick paradigm. So remember that you wanted to evaluate f at omega to the I. Instead, you will evaluate f0 at omega to the 2i, or equivalently you can think of as evaluating f0 at, think of omega square as L by 2th primitive root of unity, right. So the points have been halved, and what is the degree of f0? That is also L by 2. So the degree of f0 has been halved and the points have been halved. So truly the DFT omega has been halved. Okay, the problem has been halved. So this is the first half and f1 is the second half. And then you can combine it by just taking a linear combination of f0, f1. So that divide and conquer is now straightforward. So first you compute DFT omega square on f0. So let us say this gives you, by f0 I mean look at the coefficients of f0, that vector. So on that vector you compute, apply DFT omega square, and suppose you get E0 prime to E L by 2 minus 1. So you get now L by 2 ring elements, and the same with f1. So E0 prime prime okay. And now in step 2 you want to combine these two, that will give you DFT omega on f. So this was an important thing which you should note, that this is DFT omega square. Okay, so the primitive root of unity order has been halved here, and also the dimension on the vector space has been halved to this. So here you just merge the two solutions. So how will you merge? So you want to say EI prime plus is this all for all I?
EI plus L by 2, and then therefore EI plus
And
L by
also
2.
for minus omega.
Yeah, so this is actually only for half the i's. So up to I less than L by 2, this is okay. And for the other i's, So the ones that come after L by 2 and beyond. So these ones will give you minus sign. Okay. Any questions? So you get all from all the L coordinates. That is E0 to EL minus 1. So you have this divide step. Now you have the merge step, and that's it. So you will just output this. So the correctness of this should be fine. Right, the way this is written, it's already a proof that we just have to analyze the time complexity. Right, how many R operations does this take? So let it take TL time, TL R operations for DFT omega. Then we have the following recurrence. So the recurrence is TL is less than equal to, what is the relationship with TL by 2?
2 twice
TL by 2.
Yeah, so it is twice because there were two instances, F0, F1. Those many R operations, and the merge was around L. So that many R operations. So which if you solve like the merge sort, you will get exactly L log L. Okay, so the time complexity is L log L, many R operations. This is for our idea number 1, where you wanted to evaluate F and G. So all the evaluations are basically computing that is the same as applying DFT twice. So that can be implemented in L log L, right? And then you had idea number 2 and 3. So in 2 you wanted to multiply the values, and then in 3 you wanted to interpolate back. So let us see what happens there. So actually now at this point it should already be clear that all those steps will take similar time. So ultimately you would have multiplied polynomials. F times G is computable in L log L, R operations. So the proof is just this sequence. So you take F and you do DFT. You do DFT, so you will get F1 omega L minus 1, and on G you will get so this one is DFT omega. So this step can be done in L log L by the previous lemma. Once you have these 2L values, you will just multiply them coordinate wise. So that takes R operations. So multiplication gives you the values of h, right? So you get h at 1, omega dot dot h at omega to the L minus 1. So that is the multiplication in the ring. So that time will be how much in this step? This is only order L, right? This is the cheap step. And now you want to get back h in monomial representation, which is inverse DFT, which is again a DFT, right? So on this you apply DFT omega inverse, and that will give you h, polynomial hx. So you apply DFT omega inverse and then you scale down by L. That is a trivial step. So overall this will take L log L, right? All the steps together. So all the components now are in terms of this single operator called DFT, right? So this is a fundamental operator. Any questions? Okay, so now we have to unravel the big assumptions we made, right? Because they are nearly always false. In practice, if you take R to be complex, then you have omega present. But then saying that your algorithm takes L log L complex operations is not of much help, because computers cannot do complex arithmetic. Right? Complex numbers themselves have to be represented by, approximated by integers, ratio of integers, and then integer arithmetic has to be done. So ultimately everything has to be in bits. So saying that you have a fast algorithm in terms of complex operations is actually practically useless. So you have to get an algorithm, give an algorithm that is L log L or similar complexity in bit operations, or at least in Z operations. So this is still far from that. So we have to actually create omega when it is not there. Right? It needs some creation. So what if R doesn't have omega? So what we will do here is that we will create omega out of thin air. So what is the meaning of this? How do you create something in algebra out of thin air that doesn't exist?
By taking an extension of R.
Yeah, so you take a ring extension. So this Lth root of unity is not there in R. So you take an extension such that this gives you a virtual omega, not a complex omega, but just a virtual representation of similar properties. So consider an extension E of R. It's a ring extension. So Ry modulo. So what should you quotient out? So we have gone to the polynomial ring of R, Ry. You have to quotient out by something so that this omega gets created.
Primitive, the polynomial, the irreducible polynomial.
So first choice could have been y to the L minus 1. Is that correct? It is not the correct choice because it doesn't so all these things here are vague. but in a way, modulo y to the L minus 1, y is not, doesn't have order. It doesn't behave in a primitive way. So for it to be primitive, you want to say that y to the L by 2 should be minus 1. Okay, so you will mod out by that, y to the L by 2 plus 1. Okay. So if you look at the order of y, multiplicative order of y, element y in this ring extension E, y to the L by 2 is minus 1, L is a power of 2, so hence the order of y is actually L. I think you will also be fine with y to the L minus 1, but at this point I want to avoid that. Let us continue with this, but you could take this or you could take y to the L minus 1. So that will provide you with this virtualized version of omega, and you can talk about now y to the 0, y square, dot dot y to the L minus 1. So you can think of that set as the set of points, and you try to do everything like you did before. Just syntactically replace omega by y. Okay, but then you have to, the only issue will be in the time complexity. So you, because the time complexity, you want to say how many operations in R. So you have to carefully analyze, because you are now working with the polynomials over R. So you have to do polynomial arithmetic there above R, just to do computations in E. Okay, so we have to be careful with the time complexity analysis. So we consider E to be this, and we take omega to be now this y. Okay, that's the solution to work with omega when omega is not there. Oh, I remember. So this one property of this polynomial. So is y to the L minus 1 irreducible? It is not. Is this polynomial irreducible over Q? Yes, so this is irreducible. That's one good thing. So I want to work with this because it has this irreducibility property over rationals. Generally R will be Q or Z. So in that setting, this will be an irreducible polynomial. This also I leave as an exercise. So we'll build on this in the next class.
Irreducible over R, we should say.
Yeah, but R is a ring, so there we have to. Probably that also you can show. As long as characteristic of R is not, is odd, it should be true. Yes, so those are side observations, you can prove them as exercise. So it's very important in what we are going to do in the next class.